Hi, myself Dr. Lakshmi Devi, Professor, Department of ECE, St. Peter's Engineering College, which is located at Kompally, Hyderabad. Today I would like to cover image restoration as a second part after completion of the introduction. Part here, image restoration degradation models, noise models, special filters in order to minimize that noise. In this today's session, I would like to observe these topics. As a continuation, frequency domain filters we'll see in the next, as well as Wiener filter, constraint least square filter concepts I'll cover in the next session. Let us see image restoration. The principal source for noise in digital images arises during either at the image acquisition or at the time of transmission. These are the principal sources of noise to be added to the images. That is, image acquisition in the sense at the time of digitization or at the time of transmission of an image from place to the place, there is a chance to have noise to be added to the digital images. Then, imaging sensors are affected by a variety of factors such as the environmental conditions during image acquisition and by the quality of the sensing elements themselves. Because of the sensing elements problem also, there is a chance to have at the time of acquisition noise to be added in the images, or due to environmental conditions there is a chance to have noise to be added at the time of capturing the images. In acquiring images with a cam, light levels and sensor temperatures are major factors to be considered as a photographer. These are also affecting the amount of noise at the time of capturing that leads to some disturbance or additive noise to be added to the images. Due to sensor problems, due to sensing temperature problems or camera lens adjustment problems, all these leads to some sort of noises to be added to the images. Restoration techniques are based on mathematical or probabilistic models of image processing. That's the reason restoration process will call it as objective process. Enhancement is a subjective process. Restoration is an objective process. But both enhancement and restoration are meant for improving the quality of an image only. But still, here some mathematical or probabilistic models of image processing are involved. That's the reason we'll consider image restoration is an objective process. Enhancement, on the other hand, is based on human subjective preferences regarding what constitutes a good enhancement result. But image restoration refers to a class of methods that aim to remove or reduce the degradations that have occurred while the digital image was being obtained. So all natural images when displayed have gone through some sort of degradations. So what are the different degradations we have here? What are the reasons for degrading the image? Means acquisition mode and processing mode are during display mode. During display mode means due to sensor noises or blur due to camera misfocus, relative object camera motions, random atmospheric turbulence effects, or any other reasons there is a chance of noise to be affected to the images. Acquisition mode, at the time of acquisition, noise to be added. Processing mode at the time of transmission or at the time of processing an image, due to different steps of processings from acquisition to the storing stage of an image, there are a number of processings occurs. During any of these processings there is a chance to add some noise, and during display mode also it affects some noise due to sensor problems, blur due to camera misfocus of camera lens, and relative motion in between the object and cam, if it is not correct, then also there is a chance to introduce some noise. Then random atmospheric turbulences, because of environmental problems, there is a chance to have some noise to be added to the images or at the time of capturing of images. So image degradation model. Let us see here image degradation model, blurring caused by a finite camera exposures and blurring caused by motion, filters used in frequency domain, low pass, high pass, band pass and notch pass filters. Exactly these filters used in frequency domain that we'll see in the next video. First, here you can observe the different noise models in this video, as well as how you are minimizing that noises. What are the different filters we have? That information will cover in this particular. Let us see first the image degradation model. Degradation process operates on a degradation function that operates on an input image with an additive noise term. The name itself, the definition itself gives how you're defining actually the degradation model. It's a process which operates on the degradation function that operates on an input image with an additive noise term. So, input image is represented by using the notation f of xy. Noise term can be represented as eta of xy or n of xy. These two terms, when combined, that gives the result of g of xy. That g of xy is actually a degraded image with respect to the input image of f of xy as well as additive noise of n of xy. If g of xy is available, some knowledge about the degradation function h and some knowledge about the additive noise term eta of xy, the objective of rotation, objective of restoration is to obtain an estimate of f cap of xy of the original image. The meaning of this degradation model totally, once we have degraded image f of xy as a function of input image f of xy as well as additive noise term of eta of xy, but still it leads to the degraded image of g of xy. Then with this particular knowledge of f of xy and eta of xy, if you are in a position to extract the restored image, which we denoted it as f cap of xy. Restored image means after completion of the degradation, as an input of degradation image, if we have reconstructed the image through this restoration filter or restoration process, that particular output image will call it as a restored image. That restored image or estimated image, we are denoting here it as f cap of xy. F cap of xy, definitely it's not same as the original. Let us see here the block diagram of the degradation model. Model of the image degradation and restoration process. Let us see f of xy is an input image which is giving as an input to the degradation function. Degradation function or degradation factor you can say as a h. If you have denoted with a small h, that's the degradation factor of the spatial domain. If you are representing this as a capital H, that we are calling it as a frequency domain degradation function. So degradation factor or function h. After this degradation, then output by adding of additive noise n of xy or eta of xy, that leads to the overall degraded image, which we are denoting it as g of xy. This particular block, we'll call it as a degradation block. This one is degradation block with the degradation factor as well as additive noise. We named it as a degradation. Output of this degradation is g of xy, which is an input to the next restoration process or restoration filter. Output of this restoration we are estimating as a restored image or reconstructed image from the degraded image of g of xy. That's why we are denoting the output of the restoration filter as f cap of xy. F cap of xy definitely may not be the same as f of xy. F of xy is an original input image. F cap of xy is a restored image from the degraded image. So f cap of xy is not same as f of xy always, because once the image is undergone, any sort of noise or any sort of degradation mechanism, there is no chance to retrieve it back as same as the original image. That's the reason we are denoting the output restored image as f cap of xy only. This is the simple degradation model, and explanation of this degradation model you have to write the importance of the degradation function and importance of the restoration filters. What are the different degradation functions we have? What are the different types of noises we have? And what are the different types of filters we have in order to reconstruct as close as possible to the original or input image that we can. Let us see here. We want the estimate to be as close as possible to the original image. The more we know about h and eta, the closer f of xy will be to f of xy. That is, whenever we know the h as well as eta, the closer f of xy, there is a chance to extract through this restoration process. If it is a linear position invariant process, then degraded image is given in the spatial domain by linear position invariant process means in the spatial domain we are representing that, then that is a g of xy is equals to, it's not actually the capital, it should be the small g of xy. G of xy is equals to f of xy convolution of h of xy, where h of xy is a degradation factor, f of xy is an input image, convolution between these two plus additive noise of eta xy. If I have added, this totally gives a degraded image in the spatial domain as small g. This is small g, by mistake it's actually capital G came. Small g of xy. This is a degraded image in the spatial domain representation. So h of small h of xy is spatial representation of degradation function, and symbol, the convolution, symbol star represents the convolution process in between the input image and degradation factor. So in frequency domain, we may write the same equation as g of uv is equals to f of uv into h of uv plus n of uv. The terms in the capital letters are the Fourier transform of the corresponding terms in the spatial domain. Here by mistake given g and h are capitals, but in the spatial domain all the functions we are denoting it as small letters, and in this frequency domain all the functions, two-dimensional functions, we are representing it as capital letters, capital alphabets, g of uv, f of uv into capital h of uv plus capital N of uv. These are simple notations you should remember as a spatial domain representation of the degradation image or degraded image, and frequency domain representation of the degraded image. So now let us see what are the different noise models we have. But first, what is noise model? The principal source of noise in digital images arises during image acquisition and transmission. This already discussed. The performance of imaging sensors is affected by a variety of factors such as environmental conditions during image acquisition and by the quality of the sensing elements by themselves. So images are corrupted during transmission principally due to the interference in the channels used for the transmission. Since main sources of noise presented in the digital images are resulted from atmospheric turbulences and image sensor circuitry, following assumptions can be made, that is, the noise model is spatial invariant. That is, noise model is spatial invariant means independent of spatial location. The noise model is uncorrelated with the object function. These 2 points regarding to the noise model we should remember. Noise model is a spatial invariant. It's an independent of a spatial location, and noise model is uncorrelated with the object function. There is no correlation with the object function to these noise models, and it is also a spatial invariant. It is independent of the location that effect appears with these noise models. So here, noise models, what are the different types of noises gets affected? The first one is the Gaussian noise. The Gaussian noise is a more known noise in almost all the communication subjects we come across, like in Gaussian noise. The Gaussian noise probability density function, probability distribution function of Gaussian random variables is denoted it as P of Z. 1 by square root of 2 pi into 1 by sigma exponential of minus of z minus z bar whole square divided by 2 sigma square. So the Gaussian shape here, it appears to be a bell shape, which is symmetric from its center, that is mean value will consider as a mu here. But here representing in this particular formulas, z bar is the mean of average value of z. Z is gray level values of an image. The mean value we are denoting it as Z bar in the expression, and mu in case of figure, that is a Gaussian noise graphical representation. Then sigma is equals to, actually sigma means here the sigma is wrong here in this representation. This sigma leads to the standard deviation. So here from its mean value, what is the standard deviation with its mu minus sigma on left hand side, mu plus sigma on right hand side, if you have considered that average probability distribution function as P of Z for this particular gray levels of image, 1 by square root of 2 pi sigma, 0.607 by square root of 2 pi sigma. Values if you have considered, this is actually appears to be asymmetric on both the sides from its mean value. Based on its standard deviation, we are considering how the noise gets affected to this particular images, which is independent of its spatial locations. So probability distribution function of the Gaussian random variables is a given P of Z formula according to its mean value, according to its standard deviation and variances. It's having its effect of to the effect in its images. Coming to the next model, Rayleigh noise. Rayleigh noise is also appears to be more or less is equals to the Gaussian noise, but the shape of this Rayleigh distribution function is somewhat different than a Gaussian distribution function. So just here, this particular left side, this is a sharp, not actually the smooth as in the last symmetric curve of Gaussian. This only the deviation we can observe from the Rayleigh noise probability distribution function to Gaussian noise. So now the Rayleigh distribution is not having any symmetric because of this particular shape. It's not having symmetric. It is given by the formula of P of Z or Pz of Z. The notation may be Pz of Z or P of Z is equals to the formula 2 by B Z minus A into exponential of minus Z minus A whole square by B whenever Z is greater than or equals to A. If Z is less than A, it appears to be 0. Based on this particular distribution function, probability distribution function, we have framed this particular formula P of Z how it is. If Z is greater than or equals to A, we can calculate based on this value of A and B's, the distribution appears to be like this. Where we have the maximum means whenever the Z is equals to A plus square root of B by 2, then the maximum value of the probability distribution function occurs, that is 0.607 square root of 2 by B. Okay, this is the Rayleigh distribution with the maximum value whenever Z is greater than or equals to A. Whenever that particular Z is equals to A plus square root of B by 2, will get the maximum value. Otherwise, it is actually again it's reducing after crossing this particular value. Okay, this means the mean and variances of this densities is given as M is equals to the A plus square root of pi B by 4 is the mean, and sigma square is actually the variance that's equals to B into 4 minus pi by 4. These are some standard formulas for this particular noise models, Rayleigh. Then coming to the next one, gamma noise. So the probability distribution function of Erlang noise is given by, it's also called Erlang. Gamma noise is also called Erlang noise. The shape here similar to this particular gamma noise, Rayleigh noise, but Rayleigh noise it's moving towards origin of this particular probability distribution function. So now let us observe here the peak value of this particular gamma noise will get at the Z value is equals to B minus 1 by A. So gamma noise here, probability distribution function P of Z is equals to A to the power of B, Z to the power of B minus 1 divided by B minus 1 factorial exponential of minus AZ. For Z is greater than or equals to 0. Always here if you observe this particular graphical representation of distribution function, Z is greater than or equals to 0 means at 0 also we have certain value of this distribution function. But not like in the Gaussian and Rayleigh noise models. So here we can observe that based on that here the formula is appearing like this. If Z is less than 0, the value probably it's a P of Z is equals to 0. So Z is greater than or equals to 0 only the value is there. Whenever Z is equals to B minus A by B minus 1 by A, the value comes, then the value here the P of Z, the probability distribution function gives the maximum value which is equivalent to here the K. So this is where K is equals to A into B minus 1 to the power of B minus 1, B minus 1 factorial e to the power of minus B minus 1. That means if you have substituted the value of Z is equals to B minus 1 by A, you will get this value that we are denoting it as a K, where you will get the maximum value, that is here the probability distribution function in the graphical representation of gamma noise. The mean and variances of these densities are given by mean mu is equals to B by A, variance sigma square is equals to B by A square. These formulas are very essential to remember whenever there is a chance to have a noise models cases, there is a chance to have some problems. If you have remembered these formulas, it's a direct substitution for evaluating of any probability distribution functions of any sort of noises. Its shape is similar to that of Rayleigh noise, but it's closer to the origin. The equation is referred to as gamma density. It is corrected only when the denominator is the gamma function. Okay, the denominator is a gamma function. The more or less having similarity in between Rayleigh as well as gamma noise, Rayleigh noise as well as Gaussian, but the shape is still deviating to some extent. Then coming to the noise, exponential noise. This is totally different as compared to the loss noises and probability distribution functions of the loss noises. Exponential decay and exponential rise. We come across these concepts in the transiencies. So here exponential distribution has an exponential shape. The probability distribution function of exponential noise is given by this shape here. You can observe whenever the intensity of the pixels in a image Z is equals to 0, then the probability distribution function, the value it leads to A. That means let us substitute here. If Z is greater than or equals to 0, the value of P of Z is equals to A into e to the power of minus AZ. If Z is equals to 0, if you have substituted, here this e power term becomes e power minus 0. So e power term 0 means it's a 1. Then the probability distribution function, the probability of that particular exponential noise at Z is equals to 0, we have the maximum value as some constant, that is A. So where A is greater than 0, the mean and variances of this density are given by mean is equals to 1 by A and sigma square variance is equals to 1 by A square. In this way, you can calculate the mean and variances of the noises and probability distribution functions of a particular noises. Then coming to the next one, uniform noise. The probability distribution function of uniform noise is given by P of Z with respect to its intensities of pixels or levels of the pixels on x-axis and probability distribution function of probability of occurrence of that gray levels on y-axis if you have observed. The P of Z, that is a probability distribution function of uniform noise, is given by P of Z is equals to 1 by B minus A if A is less than or equals to Z is less than or equals to B. That itself indicates if Z is lies in between A and B, then the probability distribution function of uniform noise is equals to 1 by B minus A. Or otherwise, the value of P of Z is equals to 0. If it is lies in between A to B means within a particular stipulated period of gray levels only that uniform noise gets affected. That's the shape itself indicates. Noise is uniformly appears within a stipulated period in between the A and B of the gray levels of the input image pixels. So the mean and variances of this noise is M is equals to A plus B by 2 is the mean, and sigma square is equals to maximum value of a gray level minus minimum value of the gray level whole square divided by 12. This is actually some standard notation to follow the variance of uniform noise. So these are the probability distribution functions of the uniform noise, mean and variances of the noises of. Then coming to the last one, sixth one, impulse or salt and pepper noise. In this case, the noise is signal dependent and is multiplied to the image. So the probability distribution function of bipolar noise is given by bipolar or impulse noise or salt and pepper noise. These are all synonyms of this noise. So the impulse, it appears to be impulse in its histogram of an image. These probabilities are appears to be like impulse. That's the reason the name of this noise will call it as impulse noise, or otherwise salt and pepper noise. The reason for calling salt and pepper noise, once this noise is affected on any images, it appears to be salt noise, salt dots like white dots and black dots. So here probability distribution for gray level of the pixels, if it is greater than A and less than B, we'll consider this probability distributions of the corresponding A value as a PA, probability distribution of the corresponding gray level of B as a PB. So in between these two are actually the impulses if you have considered. The probability distribution of bipolar or impulse noise is given by P of Z. The probability distribution function P of Z is equals to PA for Z is equals to A. That is, Z is equals to A means the probability distribution function or probability distribution function as PA. That's the meaning here PA. If Z is equals to B, the probability distribution function is PB. That is, P of Z is equals to PB. These are the notations from this particular graphical representation. Otherwise, there is no any probability distribution function appears in its graphical representation. That's why for otherwise case, it's a 0. If B is greater than A, that means here you can observe if B is greater than A, what happens? If A is less than, if Z is less than A, what happens? Let us see. If B is greater than A, gray level B will appear as a light dot in image. Definitely we know that gray levels of pixels from its dark value to the bright value, it varies towards like this, towards on x-axis. That is closer to the A, or we'll consider as a dark values. Beyond B value, we'll consider as pixel values or closer to the bright values. That's given here. B will appear as a light dot in the image level. In the image, level A will appear like a dark dot. That means either at A position or less than A, the values of the pixels are closer to the darkness. The values of the pixels greater than B are closer to the brightness, or we can say light dots or bright dots. These are noise models, totally 6 noise models. These 6 noise models comes under random noise models. As an example, test pattern used to illustrate the characteristics of noise, probability distribution functions of noises. So if you observe this particular figure, it consists of 3 different colors, black, some gray level and this white. In general, the noise distribution is not recognizable by image inspection. But still, in what way we can observe, noises gets affected to these images based on its probability distribution functions. Let us see with these figures how we can guess which type of noise is affected to that particular images. This is a original image. Let us see here. These are all noisy images. That means these are all the images gets affected with the noise. That's why these are all actually corrupted images, or you can say noisy images. While observing itself, we are in a position to identify these images are degraded its quality because of additive noise. But which type of noise, how we come to know? Once we will take the histogram of these particular images, then we can easily identify this particular, based on the shape of this probability distribution functions corresponding to the histogram of gray levels appears in an image. This distribution function shapes, we can consider this one is the Gaussian distribution, because just now we come across 6 random noise distribution functions. One among those is Gaussian noise. While observing this distribution, skewness probability distribution functions affects the image at an average here given with its histograms. Based on this particular shape, we'll consider the noise. Which type of noise means? A Gaussian noise. And coming to this, based on this particular shape itself, you can come to know that this one is a Rayleigh noise. And here at z is equals to 0 also it's started the distribution of a noise that will consider it as a gamma noise. Okay, gamma noise. Now let's see figure. This one is based on the shape we'll consider. This is an exponential. This is an exponential noise. And here based on this distribution of noise factor presence in an image, it's an uniform noise. This appears to be an impulse, like 3 impulses appears because of 3 colors. One is at exactly for the 0. Here it represents the 0 impulse. And sorry, black impulse, this one, this line indicates the black impulse. And this gray level which is centered in between the black and white, that gray level impulse is this one. And this white color impulse is this. White color, pure white color, here if you observe, this one is an actually not this shows actually the combination of this particular gray levels. Here this impulse appears and this one is a pure white. In this way, just we are in a position to identify which type of noise is affected to the images based on its probability distribution functions. We are in a position to identify the types of noise through the histograms of affected noise affected images. Now, restoration in the presence of noise only if we have considered, then what type of filters we can use for minimizing of that noise? There we can use the spatial filters. So already in the first hierarchy of restoration, under the noise we come across random noises as well as periodic noises. Under these random noises, just now we discussed the 6 types of random noises. So whenever the images gets affected with this particular random noises, what are the corresponding filters may support for minimizing of that noise? That filters for minimizing of a random noise will use spatial filters. For minimizing of periodic noise, we'll use frequency domain filters. For minimizing of random noise, we'll use spatial domain filters. This point you should remember. For minimizing of a random noise, which type of filters we can use? Spatial filters. For minimizing of periodic noises, which type of filters we can use? Frequency domain filters. This is the basic difference between the spatial filters to the frequency domain filters. Now let us see here. If the images gets affected only with the noise, any sort of the noises which we discussed till now comes under the random noises, then what are the measures for minimizing of that noise through these spatial filters? That is our aim here. When the only degradation present in an image is noise, then without having any degradation cause, only through noise if the image gets affected or gets deteriorated, means how you are defining the degradation model equation or degradation of an image, in the sense g of xy is equals to, this is also small g please, g of xy is equals to f of xy plus eta of xy. Here h of xy degradation factor is missing because we are not considering any degradation mechanism. It's only affected by noise, means this is actually the formula. The corresponding spatial domain formula is this. The corresponding frequency domain formula is f of g of uv is equals to f of uv plus, this is capital F, f of uv plus capital N of uv. The noise terms are unknown, so subtracting them from g of xy or g of uv is not a realistic approach. That means noise no one can predict. These are unknown in general. So subtracting of this from g of xy, that means g of xy or g of uv is not a realistic approach in order to extract the original image or restored image. That means in the case of periodic noise, it is possible to estimate n of uv from the spectrum g of uv. But in spatial domain, it's not so easy to extract the noise image or noise signal n of xy or n of uv. So n of uv can be subtracted from g of uv in order to obtain the estimate of original image. In the spatial filtering can be done when only additive noise is present. That means without considering the degradation factor H, if you have considered the image is deteriorated only by the noise, then G of UV or G of UV is equals to f of UV plus n of UV. That means f of UV is equals to G of UV minus n of UV only. That means whenever if you have subtracted n of uv from the g of uv, you will get f of uv. But that f of uv, if you have considered noise models, then that's a possibility to have n of uv, f of uv is equals to g of uv minus n of uv. Okay. Now, what are the techniques used to reduce the noise effects? Whatever the noises we discussed. How to reduce that noise effects? Here you can see different filter mechanisms. So basically we have two types of filters for minimizing of all these random noises in the spatial domain. One is mean filters, second one is order statistic filters. In this particular video, we'll see these two filter mechanisms for minimizing of random noises in the spatial domain, like mean filters. What are the different types of mean filters we have? Arithmetic mean filters, geometric mean filters, harmonic mean filters, contra harmonic mean filters. These categories already have given in the first introduction of restoration hierarchy. So first let us see arithmetic mean filter. It is the simplest mean filter, and how we are performing this filtering operation on the original image. Just here I can explain clearly. Please listen carefully. So let us consider sub-image of the original image as S suffix xy that represents set of coordinates in the sub-image. Sub-image size, let us see. Here I have given 3 by 3. So sub-image size also you can choose 3 by 3 of size, that we are denoting as small m by n. In general, capital M by n we are representing for original image rows and columns. This is small size which you are choosing for a mask or as a sub-image. The size we are denoting it as with a small m by n. Centered at point xy. The centered point is xy. The arithmetic mean filter computes the average value of the corrupted image g of xy in the area defined by sxy. Now, arithmetic mean filter, how you are computing means, let us see. F cap of xy is equals to, because in the degradation model already we come across the first we have degradation function h, then that particular output is added with the noise n of xy. Then output of this additive noise we have g of xy. G of xy have given as an input to the restoration filter. Restoration filter output is we have already denoted it as f cap of xy. Because of filter mechanism, output of this restoration filter will see f cap of xy is equals to 1 by mn. This mn are size of the sub image which you have selected. So m by n or mn here. 1 by mn sigma st belongs to sxy. That is, st is a spatial location of that sub image of the pixels. We are representing it as st. That belongs to sxy. Sxy represents the coordinates of the subimage. So st is one of the coordinates of the given subimage of sxy. G of st. that is the G of ST, that is input of the degradation, input of restoration filter is G of XY. We are performing this operation by considering the subimages of SXY as coordinates ST. That's the reason input is just we are representing as in terms of that spatial locations G of ST here. So in such a way, if you have considered just sigma of mean of this, that means the sum of this all the coordinates divided by the size of that particular subimage. Sum of this are all the coordinates means sigma G of ST. For all the coordinates, we have taken the sum of the values of all the coordinate pixels divided by the size of the subimage, which we are considering it as m by n. That gives f cap of xy. The mean filter here given for 3 by 3 size 1 by 9. That means this 1 by 9 is a common for all the things, and the filter coefficients are 1, 1, 1, 1 given. Filter means the subimage, and when overlapping of this filter, it's an actually gives an output of the mean filter. It's an average, or we can say the mean filtered value to be replaced by center pixel value. In such a way, we can compute for all the pixels. The second mean filter is geometric mean filter. An image restored using a geometric mean filter is given by the expression f cap of xy is equals to pi st belongs to sxy g of st to the power of 1 by mn. So here each restored pixel is given by the product of pixel in the subimage window. Subimage means the same size of 3 by 3 we will consider. STs are spatial locations of the subimage. SXY is an actually subimage size. So G of ST is an degraded image for this particular spatial location of subimage we are representing as G of XT. The product terms, product of the pixels in the subimage window raised to the power 1 by mn, that gives the output of a geometric mean filter f cap of xy. So geometric mean filter, but it loses image details in the process. So whenever I have performed the first arithmetic mean filter, the output of the arithmetic mean filter can smoothens the image. That means the blurriness appears in the image, but it reduces some noise. But in this geometric mean filters, it loses image details also as compared to the arithmetic mean filter. Geometric mean filter here, the function will this function will filter the image by the nonlinear geometric mean method. This method works for only monochrome 8-bit per pixel and 24-bit per pixel images. Based on the type of depth of the pixels, it works well for that particular type of images only, the geometric mean filters. The geometric mean filter is a member of a set of nonlinear mean filters which are better at removing Gaussian type noise. When we can prefer these geometric mean filters means for removing of Gaussian type of noises and preserving edge features than arithmetic mean filters. Here the smoothness is less compared to the arithmetic mean filters in the geometric. Here the original image 256 by 256 pixel image corrupted by additive Gaussian noise, and the geometric mean filter image using a 3 by 3 pixel square mask we have evaluated from this input image of degraded image to the processed image through this restoration. Sorry. Next one, harmonic mean filter. The harmonic mean filter operation is given by the expression f cap of xy is equals to mn is again size of a subimage rows and columns mn by sigma st belongs to sxy g of st. So the harmonic mean filter works well for salt noise but fails for pepper noise. It does well with Gaussian noise also. When we can prefer this particular harmonic mean filter means whenever Gaussian noise is affected, it works well good for Gaussian noise, but With this harmonic mean filter, we can effectively minimizes the salt noise, but it won't minimize the pepper noise. So based on our application, we can make use of any of these filters based on effect of noise appears in the images. So the next one, contra harmonic mean filters. Contra harmonic mean filter, a restored response is given by f cap of xy is equals to sigma st belongs to sxy g of st to the power of q plus 1 divided by sigma st belongs to sxy g of st to the power of q. So Q is the order of the filter, and adjusting its value changes the filter's behavior. Based on this, if positive value if you have chosen for the Q, then it eliminates very effectively the pepper noise. Negative value if you have assigned to the Q, then it eliminates salt noise. Based on type of noise affected in the images, we can choose the values of the Q. Accordingly, it minimizes either salt noises or pepper noises, which is effectively we can use in case of impulse noise. Whenever the impulse noise present, this contra-harmonic mean filter based on intensity of either salt or pepper noises, have to choose the value of the Q. So in this way, we can minimize all types of random noises. Once it is affected to the images, we can minimize with this all filter mechanisms, which we'll call it as a different restoration filters, if noise only affected to the images. Okay, I hope you are in a position to understand. But after completion of the mean filters, other statistic filters are also there for minimizing of this type of noise models. Let us see here. Other statistic filters are spatial filters whose response is based on ordering the pixel contained in the image area encompassed by the filter. The response of the filter at any point is determined by the ranking result. That means based on ordering of the pixel values presence in a size of an image or presence in a size of a chosen subimage, we are going to extract uh, the values, or we are going to extract the quality of images through this order statistic filters. That's the reason these filters named it as order statistics filters. Let us see first one, median filter. The name itself gives a median value. In the best, it is the best order statistic filter. It replaces the value of the pixel by the median of gray levels in the neighborhood of the pixels. Median of the gray levels in the neighborhood of the pixels. How it performs means, let us consider 3 by 3 subimage if I have chosen, and performing that particular 3 by 3 size for replacing each and every center pixel value. So first you can keep 9 elements or 9 gray levels in an order, either ascending order or descending order. Then 9 values, in the sense definitely we have the middle value. The middle value should be replaced. That means a center pixel value of that subimage to be replaced by the middle value of this ordered gray levels of the values. Gray levels of the values. That's the reason it's called actually the median filter. It provides, that is formulated as f cap of xy is equals to median of a subimage size of st belongs to sxy g of st. Order to be placed, then center value have to consider and replace the center value of a window or a subimage by its median value. It provides excellent noise reduction capabilities with considerably less blurring than smoothing filters of similar size. It's not then, it's than smoothing filters of similar size. So definitely here the blurring effect is less as compared to the smoothing filters, or you can say arithmetic mean filters in median filtering concept. Let us see the next filter on statistic filters. Max filter, min filter, midpoint filter. These are the filters. Let us see now here. First, max filter. Using the 100th percentile of a ranked set of numbers is called the max filter and is given by the equation. So f cap of xy is equals to max of st belongs to sxy g of st. We have already placed the order of elements, 9 elements present in the subimage. The 9 elements once you have placed means it's have the maximum value to the minimum value. So maximum value, if you have replaced all center pixel value to be replaced by its maximum value of the ordered gray levels, that particular filtering we'll call it as max filtering. Then it is used for finding the brightest point in an image. Brightest point in an image means max filters we are replacing with the maximum values. Then there is a possibility to identify brightest spots very easily with this results of max filters. While coming to the min filter, the 0th percentile filter is min filter. 0th percentile filter is min filter means already you have arranged the 9 gray levels of the sub image in an order. The maximum value if you have replaced the center pixel is max filter. If you have replaced with the minimum value, that we will call it as min filter. How we are denoting that means f cap of xy is equals to min of st belongs to sxy g of st. This filter is useful for flinging the darkest point in image. Because we are replacing all the pixels with this min values, that's the reason. It's very easy to extract, that is flinging the darkest point in an image with this particular min filter operation. Then last order statistic filters are midpoint filter. The midpoint filter simply computes the midpoint between the maximum and minimum values in the area encompassed by the subimage. So f cap of xy is equals to the maximum value of that list plus the minimum value of the list divided by 2 gives midpoint filter. This filter works best for randomly distributed noise like Gaussian or uniform noises. So these are the different types of mean filters as well as order statistics filters which are meant for minimizing of random noises appears in the images. I hope you are in a position to understand the better way of different noise models and what are the filters we can use for minimizing of that. Here I have given just an example. If image is corrupted by salt and pepper noise with the probabilities of P and PBs is equals to 0.1. So here if this is an actually image, a corrupted image with its probabilities 0.1, P and PBs. Now the resultant image is B. That is resultant of one pass with a median filter of size 3 by 3. Median filter if you have passed this particular corrupted image, then these are the results. The result of processing this image if you have passed through this filter again, that is result of processing B with this filter, again this is actually the response. The same result of processing C with the same filter, this is actually the response. That means this is an input to the actually the filter again with the median filter, and this is an actually input again for the median filter. Still we are observing in these cases minimizing of that noise and maximizing the clarity. Okay, this is an actually example. Now example, here by observing these two images we are in a position to understand result of filtering. This A is with a max filter of size 3 by 3. This result of filtering B with a min filter of same size 3 by 3. With the max filter means most of the white dots are more visible in the max filter, but most of the black dots are more visible in this min filter. And then we can observe this all the thicknesses are reduced in the max filter, and here the thicknesses are increased. That means the black portion wherever it appears, it becomes thick in case of min filters. Spots appears, that improves in case of max filters. Okay, thank you. With this, I hope you are in a position to understand the total different random noises appears in the restoration process and measures for minimizing of that filters with the filters of mean filters as well as order statistic filters in the spatial domain. Thank you.